Hello folks, I'm going to talk about mathematics, about transitioning from nice, simple, pleasant, happy-go-lucky mathematics to serious mathematics. Not banker serious, but relevant mathematics. And so, to start with, a lot of our class 8, 9, 10 to class 11, 12 math, lot of it has got to do with calculus in some form. And so, calculus and around calculus. So, the topics around calculus are where you use calculus in order to get better at cracking those topics, right? So, like conic sections, right? So, but on trigonometric equation, but the big backbone of chunk of things is calculus, right? So, and in calculus we talk about differentiation, talk about integration, and so very often we talk, lots of students, they know what d by dx of sin x is, they know d by dx of sin x is cos x, they know integral is the kind of opposite of differential, but very often they don't know, hey, what exactly is happening here, what exactly is differentiation. They've heard the words, they've heard the buzz phrases, differential is just slope, differential is the tangent, differential is what happens at the increment, integral is area under the curve, definite integral is measured, indefinite integral is definite integral is between two points, indefinite is open-ended, all of that, but very often they're just buzzwords. And so, and that happens because the intuition about what this more serious math is goes away. And so, I think ideally differentiation we should come to by talking about limits, continuity, differentiability, then differentiation, then integration. That should be like the sequence. Like we should kind of segue into this through this. Right? So, very often I think the school syllabus or the curriculum focuses on this and rushes to that and makes d by dx like an operator instead of it being a very organic thing to go here. It becomes something that's just tacked on, and which makes the comprehension of this difficult, and the intuitive backbone is not there. And so, more than that, I think this alone is not sufficient. Right? In many ways, calculus is the culmination of many strands of learning, and I'm going to break this into two parts. Right? Going into learning calculus intuitively, this is one giant structure from the algebraic world, one giant structure from the geometry visual world, and then once these ideas are kind of digested really well, we tack on notions of algebra and curves and graphs, and then talk about limits, continuity, differentiability, and kind of going into differentiation, integration. That's the theme. So what goes prior to this is this, but what a ton of stuff goes before that. And so I have two tracks for that. One I'd call the geometry track, one I'd call the algebra track. And so the algebra track prior to this is functions. Functions really sets the sets and functions, set theory and functions really sets the base for thinking about an input variable and an output variable for a graph, for thinking about x and y, for thinking about x and f of x. And so that idea is very powerful. And so, but before we jump into functions, we need to do a ton of quadratic equations. And we start getting comfortable with the idea of diagrams and drawings and x's and y's. We do quadratic equations to build on that. In order to reinforce the algebraic point, we need to do inequalities. Basic inequalities, not fancy inequalities, because in functions you're going to talk about domain and range. For that, inequalities plays a role. Right? Prior to quadratic equations, long before that sits linear equation. This is very simple stuff. You need to digest this before going there, but that's way into the path that we don't really need to worry about. Right? On this side, we have kind of a very powerful understanding of trigonometry, coordinate geometry is needed. Sitting behind this is geometry. Without really getting a good handle on geometry, congruence, similarity, and that set of ideas, you cannot go deeper into either trigonometry or coordinate geometry. And coordinate geometry is taking geometry and adding a language of algebra to it. And trigonometry is taking geometry and amping it up for specific cases, specific ideas, and then building on those ideas independent of the strands of geometry on which it was built on. So the geometry and linear equations are further into the past. We finish in class 6, 7, 8, 9, but then you need to take that at these layers and add this to really get comfortable with the more, be aware of a ton of things to go into this. It's not sufficient because once you learn functions and you learn geometry, trigonometry, quadratic geometry, how functions are drawn, and you need to have a beautiful bridge between the algebraic world and the visual world, which is graphs come in. We talk about, introduce the idea of slopes and all that, where we bridge these two, the visual world and the algebraic world. And how is x square minus 4x plus 5 a shape like this, which is why a powerful understanding of coordinate geometry and functions need to come together for us to talk about graphs and slopes, and then we need to add on that to then talk about limits and continuity, then go on to differentiation, integration. Right? So this you need to have a ground grasp of this, sound grasp of this, put these two together. When we start talking about graphs and slopes, we need to introduce a couple of specialized functions. We need to talk about exponents and logarithms. They are good functions, important functions, and graphing them and grabbing onto them becomes very important. And then we talk about trigonometric functions. From a visual graphing point of view, therefore, from there going on to differential ideas becomes simpler. And so, anyone who's saying, "Look, I'm interested. I need to have a sound handle on the more serious mathematics. It's mathematics that we typically see in class 11, 12, or we see in JEE or in AP calculus, what is called as pre-calculus or calculus, the more serious math. And so, has to be very careful and not rush into this. And the understanding of differentiation and integration has to be very organic, very much you get a handle on this, put both of them together to do graphs and slopes, add a little bit of trigonometric functions, add some functions, exponents and logarithm. Maybe beyond all this, you think about sequences and series, little bit of complex numbers. Why complex numbers? Because they take off from quadratic equations. Why sequences and series? So that you get comfortable with x's and y's. And these are not particularly relevant, but they're useful. And so these two I won't say are super crucial, but these three or these two and bringing them together with graphs and slopes, super crucial. A very powerful understanding of quadratic equation, then polynomials a little bit. Functions, everything about functions. You need to have the bedrock of functions very powerfully kind of in place. Then inequalities, so that you can think about functions and domain and range and all of that. Then just side from geometry, go into trigonometry and coordinate geometry, understand shapes and diagrams, understand the building blocks of that. Put both of these together, talk about graphs and slopes. Then say, hey, what happens if the graph is a little unusual? It's very easy to calculate slope of 2x plus 3y equal to 17. What if you're dealing with x square plus 9x plus 14? What if you're dealing with sine 3x? Then what happens to the diagram? Then what happens to the slope? Then how can we simplify life algebraically when you have to calculate slope? Ergo limit. Then we have a calculate the idea of limit. Then what kind of functions can have limits? Then come back to this and reinforce that. And so lots of times, because we rush into this, we hustle through this, we fail to spot the underlying links between functions, the visual way of functions, graphs, and slope after that. And so, and that makes calculus all overly formulaic, and then just a bunch of rules, find the product rule and division rule and bunch of formulae for differential, and that's it. Then carry on and run away from that. And so there's an insufficient grasp of how powerful and how brilliant this entire field of mathematics is. And so, I think a lot of people who are looking to do more serious math should first aggressively, vigorously reinforce this and put together this, so that you're ready for this. Very often I think calculus is simple enough, but the background is not ready to receive that, and therefore calculus feels cripplingly tough. And we add layers to calculus, right? So we start using calculus and finding slopes and normals and all that in coordinate geometry, and then doing more complex stuff. And so from here on in, there's more stuff to do. If this understanding is not intuitively powerful, then we're in trouble. And so anyone looking to do more serious mathematics should do all the reinforcing parts before jumping into calculus. Fine. So please definitely do that. Best wishes. Hello folks, we're doing doing it again. Hello folks, if you're thinking about doing more serious mathematics, then calculus is very central to that. So when we're talking about calculus, sometimes we think about calculus like an operator, d by dx of sin x is cos x. And so that's it. And what sits underneath that becomes fuzzier and fuzzier as time goes on. And so the way to approach that is not to aggressively study calculus, but to reinforce a bunch of topics before that. Foremost among them, quadratic equations, functions and inequalities, the algebraic end of it, trigonometry and coordinate geometry in the visual end of it. Put both of these together and talk about graphs and slopes. Then add trigonometric functions and exponents and logarithmic functions. Round it off. We build all of this so that from that base we can go into limits, continuity, differentiability. If you do it in that sequence where you put everything together around calculus, which preceding calculus, and so what is famously called as pre-calculus, then the journey seems far more natural. And so what we're doing is doing all of this in a kick-ass course called Pre-Calculus Bootcamp. Best wishes. Hello folks, if you're sitting and thinking about what next, and you're thinking about, look, I need to sign up for a bunch of these competitive exams, your JEE typically, and I need to really amp up my math, physics and chemistry, and I need to really amp up my mathematics. And a ton of mathematics is going to surround around difficult ideas, which is calculus and conic sections and whatever not. Find lots of heavy duty math starts from calculus onwards. Right? So the step up from ratios and percentages to calculus seems like a giant leap. You need to bridge that. Very, very important to understand the intuitive basis for calculus before doing the formulaic parts of calculus. The intuitive basis for calculus gets reinforced from the algebraic end. Calculus is a beautifully powerful tool which talks about which kind of marries and brings together an algebraic manipulation to visual ideas of slopes and graphs. So two parts to it. And so you need to get a powerful handle on simple ideas of trigonometry and coordinate geometry, get going on quadratic equation, functions and inequalities, bring them together to talk about graphs and slopes, then add a couple of exponents, couple of functions, exponents and logarithmic functions and trigonometric functions. Kind of warm your way very naturally into talking about graphs, functions and slopes, and therefore go towards limits, continuity, differentiability, and naturally go into differentiation. And that should be your path. So anyone who's saying, look, I'm interested, fascinated, ambitious, drawn towards this tougher part of mathematics, do not say I'll do 10 questions from differential calculus, 15 questions from integral calculus. Say I'll beef up all of this in order to be ready to grab this intuitively. That's super crucial. Otherwise, calculus becomes like this giant ball which crushes you. And so learn calculus more, go towards calculus more organically by doing all of these things around calculus. Best wishes.